So go to webinar. As a default, your microphones and webcams are muted and turned off. Also, the toolbar questions can be used to ask your questions, and the chat can be used to answer our questions. We will have a poll during the webinar just to interact with you guys a bit. So we will actually try to start that process immediately. So just a sec, we'll launch the first poll. So the first question is basically, what kind of structures are you more familiar with? Collecting responses, that's good. I see a lot of buildings. I would say 50%. 80% has voted, that's good. Okay, so kind of a mixed audience. We have a lot of people familiar with buildings, some with bridges, civil structures, and yeah, exactly. Good, good, good. Okay, so we are not completely done with the poll, just a few more questions. The second question is, how many years of experience do you have in your profession? So feel free to answer. Okay, we got an experienced audience here, Daniel.
It's pretty good. It's pretty good.
Yeah. So like I said, an experienced audience, which is good.
Yes. Good.
Always nice with people that have worked in the industry for a long time. Okay, so the final question before you will start listening to our voices. And that is, what commercial FE software do you use today when performing a dynamic analysis? And I've tried to cover a few of them. Unfortunately, no other option. So make sure you can find a suitable alternative. Okay, I think that's good. We shared the last poll, and then you guys can actually relax and sit back and basically listen to us. So we have your answers, a lot of FEM-Design, a bit sophistic, LUSAS, and SAP, which is good. So, yeah. Okay, thanks a lot, guys, for answering and interacting with us. As I said, now you can sit back and try to come up with suitable questions. So a bit about us and the idea behind this webinar. So basically, I'm working at StruSoft with bridge applications for the Swedish market. And as you may know, as a software company, the role is to provide engineers today with suitable tools to perform structural analysis and design. Daniel, on the other hand, is representing the academia, and one of their many roles is to improve the guidelines and norms that engineers work with on a daily basis. Me and Daniel have been having a lot of discussions recently, mainly about bridge dynamics, and especially the Folke Bernadotte Bridge, because it's one of the newest bridges in the city we live in. Also, we have been comparing a lot of results, usually me asking Daniel the questions about the eigenfrequencies and so on, because he had been doing a lot of his research dedicated to this bridge. Recently, however, he started to ask me questions, and one of them was, is it possible to perform a sensitivity analysis in FEM-Design for the boundary conditions? And I was very intrigued and wanted to give it a try. I did not have a clear idea on how to approach the problem, but I for sure knew that the FEM-Design API could help me, and more specifically, the guys in Gothenburg that are working with our API development. So basically, that's how the idea of this webinar came. Daniel, if you have some more stuff to add, feel free.
Well, I think the whole idea of the webinar and having collaboration between the industry and academia, I think it's pretty good. I think it's one of the main objectives of the Royal Institute of Technology of KTH to actually spread knowledge and to promote this kind of collaboration. It's important for us to have a strong bond with the industry, and as you said, to compare results and improve the current decision making. So, happy about it.
Perfect. So you have some raw data about us, but yeah, that's the hard part. We are more than only those words you are looking at. So the agenda of today: structural dynamics for pedestrian bridges. We will go through the introduction, some objectives, background, the case study, which is the Folke Bernadotte Bridge. So problem formulation, boundary condition, and the dynamic analysis. And finally, you guys can ask your questions. So the objective is to develop your professional skills in structural dynamics as a bridge engineer in FEM-Design, and to improve your decision-making process when performing a dynamic assessment of bridges. We will go through the load model according to SETRA. We will perform a sensitivity analysis of the boundary conditions by the FEM-Design API, and perform a dynamic analysis with direct time integration methods. Also, we will verify our results from the finite element calculations with simple hand calculations presented by Daniel. So Daniel, please give us a brief intro about the background of the norms.
Right, thank you, Shahal. So a bit of the background now. So we're going to discuss pretty much how do we make the dynamic assessment of a footbridge. And in order to do this, I think it's important for practical engineers to get a background of the design guidelines that you have available today. So pretty much you have got the Eurocode, you have got the SETRA, which actually pretty much the Eurocode right now is based on the SETRA. Then you have got the bridge standard, one of the pioneers in footbridge dynamics, I would say. Then you have got the FIB, which is pretty much the mobile code, and that was also a pioneer based more into the idea of the moving harmonic load problem. And then you have a very interesting one, let's say the concrete center, and that one is quite interesting, especially for our audience that it's based more into buildings, because pretty much the design guidelines of the concrete center divide pretty much treat footbridges as low frequency floors, and they have a division for the high frequency floors as well, which they pretty much changed the way in which the dynamic assessment is based. But let's just go to the basics now. So pretty much the SETRA and the Eurocode in this sense, what we're looking forward to do is to pretty much establish an equivalent state response that is representative of the actual crowd load event. And well, this is quite particular, no? Because it's not like the practical engineers will actually model moving pedestrians around and making a strong simulation about it. No, we would like to. You guys would like to make a decision. You guys would like to make an assessment that will allow you to improve the decision making, to make the dynamic assessment of your structure rather in a representative way and sort of easy to do. No? So that's the equivalent steady state. And the main idea about it, so pretty much the Eurocode and the SETRA right now, what they do is that they maximize the dynamic action, so the dynamic load that is being applied to the bridge. And that's pretty much made by applying the load that follows the mode shape. So pretty much you have at the right side, pretty much the classical figure that you can see in the Cetra, in which the load is applied following the mode shape. And as long as you follow the mode shape, pretty much the sign between the load and the mode shape, they are pretty, they're going to be, the product will be positive. So pretty much everything is adding up. So in that way, you're actually maximizing the action, so maximizing your modal load. And then we say, well, we are creating an artificial load case now, because there's no way that the crowd would actually pull off your bridge, no? So that's quite odd. Well, but actually maximizing the steady state response, which is something that is incredibly easy to find, and making the steady state response actually representative of an actual simulation of a crowd load event, well, that one might actually give you an insight and will allow you to make a decision upon the serviceability limited state of your footbridge. So yes, this is pretty much the background that we're going to use, and of course the most important quantity at this moment, it will be the acceleration, because we are checking serviceability. So, yeah.
Okay, good stuff. I know I always have a difficult question on this topic, and that is, Daniel, do you have a nice way of giving me a physical interpretation of the load shape, which, like you said, doesn't really make sense intuitively? So I'm going to let you give it a try to explain it.
Yes, thank you. So, well, pretty much the thing is that you guys are proposing a load case as an area that is not completely physical representative of what's happening. And well, if we try to go a bit further on, also we have. So actually, Shahal, we have a nice experienced audience. So I think we could sort of increase the level a bit. So pretty much, if you compute the mobile load, so if you actually compute, let's say in a continuous formulation, it's the integral of the mobile load, you would like to maximize the action. And when you do that, well, you pretty much come up with the same Cetra approach, which would be following the mode shape. And as long as you follow the mode shape, you are actually maximizing the mobile load applied. So that is, in your projected single degree of freedom representative of the mode, you will maximize the applied projection of the load. That is your mobile load. And well, this is pretty much done by applying a force that follows the motion.
Nice. I really like that explanation. That's why I didn't hesitate asking the question. Okay, so jumping on to the case study, the Folke Bernadotte Bridge, located in Stockholm. Love to travel by it, so I can take some nice photos of it. It's around 100 meters long and consists out of steel, actually stainless steel, and it has a bridge deck made out of timber. The geometry consists of circular hollow section, rectangular hollow section, and U profiles. And finally, the boundary conditions are made out of bearings, which we will definitely look more into detail later. But I just want to show you guys the model in FEM-Design and how it looks. So we will rotate around a bit. So it's made out of beam elements, and the deck is modeled with covers, which is basically a load-bearing element that only distributes the forces from the deck and does not add any stiffness. We will also have a look at the support conditions. And it is a very special support configuration because it has a triangle at the ends, which also change in height. And it's a continuous system. So you could say it's a 3-span bridge, which will give this a very special behavior, more or less like a clamp system. Basically, this support will take compression loads and these supports will take tension loads. What else is nice to add? Do you have anything in particular, Daniel?
Well, I would rather say that the case study that we have here, it's very particular, specifically due to the boundary conditions. So we have a three-point boundary condition at the end of this bridge, which makes it quite unique. Certainly not intuitive. Well, one of the most important things to see just from the structural engineering perspective. So guys, we can increase the level. So from the conceptual design point of view, you would see that there's quite a high difference between the upper line of the supports and the lower ones as well. So that's pretty much giving you a level arm, and you know you will have pretty much by just looking at the geometry, well, rather a high rotational stiffness there. So you would actually expect from the conceptual design idea. So pretty much the idea in the background when actually pretty much making this project, so coming up with an idea, well, you know that the bridge won't, it's far away from something like a simple supported beam, no? So it can't be something of that kind. And I think that's one of the most important things to mention in this particular example.
Perfect.
So, yes.
Yeah, totally agree. Okay, let's jump on to the next slide. So the problem formulation. You can give it a go, Daniel, but I have a nice question for you here as well.
Great. So the problem formulation. Great. So well, pretty much before starting with the conception, with the concept of dynamic analysis, well, we need to point out one of the, let's say, the important parameters. No? So first of all, footbridges, it's likely that you will deal with a lightweight footbridge. And well, this is quite important, and this is why I'm going to just point it out, of just going back to the fundamentals. No, I think that's always good. So if you have a lightweight structure, in our case, a lightweight footbridge, well, that actually means that you will have a very small or quite small modal mass. So you guys need to remember that accelerations are inversely proportional to the modal mass that you will get from your single degree of freedom. So, well, that pretty much tells you that if you have a lightweight structure, well, it's very likely that, let's say, the system response, the dynamic system response, that would be your accelerations, because I'm literally just going to speak about accelerations at this moment because that's the criteria for our decision making right now, will very much be affected by the fact that it's a lightweight structure. And that's just one part of the story now. Because the other part of the story is that, well, pretty much the mass is related to the frequency. We all know pretty much the classical equation: stiffness is equal to pretty much the mass times the square of the circular natural frequency. We'll see that in the later slides. And pretty much if you change the mass, well, you are affecting as well the frequencies. The second aspect that I would really like to point out is that we're pretty much dealing with a lightly dampened system, and this means struggles. So this pretty much means that we don't have the high dissipation capabilities because we're pretty much having a very low damping ratio associated with, let's say, that out. And well, that means that, well, it's going to take a lot to actually the structure to pretty much achieve a steady state response. But it's going to make our structure quite sensible, no? Because again, accelerations are inversely proportional to the damping ratio of the system. So, well, these are quite two important aspects to deal with. Well, and then we have got serviceability and a dynamic assessment. So we need to check the serviceability limit state of the structure because we would like to have a structure that pretty much satisfies the comfort criteria. And well, in that sense, you will need a tool. No? So you need the tools to actually make this dynamic assessment. You need a tool to assess the dynamic behavior of the system, to characterize the system, and pretty much get an idea of how the system is behaving. So this is pretty much from the concept point of view. So from the, let's say, from the perspective of the problem, so from the perspective of the loading, you've got walking loads, you've got running loads, then you have the crowding load event, which is pretty much maybe the most important one. The things that how are we gonna assess this particular input load that is having our system, and then we need a criteria. No, so we need to improve our decision making as a structural engineer. We need strategies to actually assess this kind of problem. And well, you have here like different, let's say, different approaches. No? So let's go for the first one. So pretty much you could have some dynamic solution that's pretty much increasing your damping capabilities. Classical TMD, a TMS damper with pretty much the AV energy of your system. These viscous dampers as well. Then you have got the mass. You can pretty much increase the mass, but that's rather an expensive solution, isn't it? And you may need to be careful now, because again, you will vary the frequencies, the natural frequencies of your system, so your rating frequencies, and well, you may be penalized by the code in that sense. So you got to be careful on that. And then you have got the stiffness. Starting the stiffness is actually changing the natural frequencies. You like to change this natural frequencies. So you have got this particular strategies, and yeah, I think we can go.
Nice. I have a good question here, and I wanted to ask you how the problem formulation for the Folke-Bernadotte bridge arrived, but I will want to go to the next slide because I want to say that it has something to do with this. And this is basically the boundary conditions and the configuration seen from above and the side. And as you see, very short spans in the end and a quite long intermediate span. And also we have these, let's call them in plane bearing supports, which makes this bridge not able to move, or at least not to move too much. And this is actually the parametric study we will investigate. But how did the idea of this come up in your world, Daniel?
Well, for me, it's quite personal. As a person that is living in Stockholm and running around, I actually passed by Djurgården, a fantastic place. I would recommend it. And then I saw the Folke-Bernadotte bridge. And well, as a person that is doing the PhD in lightweight structures and looking at this, I would say a fantastic bridge, very, very long. I would say for a footbridge that's around 100 meters span long. That's going to pretty much give you some problems in the frequencies, especially from the design perspective. And then when I pretty much saw it, that is a 3D truss structure, so a 3D truss-like structure with stainless steel. Well, I realized that yeah, this particular project may be a potential case study. And yeah.
Nice. So what we will look at is how we can vary the parameters of the longitudinal stiffness, the support stiffness. So the green line or pile through the FEM-Design API. And I will show how I've done it. I will not go into details because a colleague of mine, Johanna, had a very brief and thoroughly webinar about this topic where she went through it row by row. I will just show you guys how I've been manipulating the script, and basically what I've been doing is to modify the KX through the API. So I've prepared a model, created a StruXML file, and telling the API to enter the KX and modify the parameter. So I will show a quick view of how it looks. This is the sample prepared by Johanna, and you guys can download it on the GitHub. It's open source, so if you are a bit interested in this, make sure you give it a try, because I think for sure this will be interesting to do on any kind of structure, even if it's a dynamic analysis or a static analysis. So basically, I have the StruXML file prepared, which is the Folke Bernadotte bridge. And I will just show it again. It's this file, but in its raw format, which is the StruXML. And then I am telling the API to enter support 3 and support 4, and to iterate over different values on the support value. So I'm using this math_pow, which is 10 to the power of alpha. And I make an iteration. I make an iteration where n is 20, but in this case, I will just show where it's n equals 1 because the loop will take too long time to simulate. And then I perform the eigenfrequency analysis, and I collect the first mode of vibration, which I know is the vertical one. And then I plot a graph, which we will look at later. But let's see how this script looks. I will just give it a start. So Daniel, I got a question from the audience if the sound could be improved on your laptop, but I'm not sure.
Oh, maybe.
I think
Is it better right now?
Yeah, I think it's good. There were not too many people asking the question, so maybe it was just difficulties on one platform. So what is happening now? I will show you guys in the parametric study webinar. Basically, output files are created and the analysis is performed. Now we will see the text file that is the final. What we can say is that this is a dynamic evaluation, so I'm performing an eigenfrequency calculation. But since you don't need to add any load to get your eigenfrequencies, you just need to convert the dead load of the structure. This is an analysis you can perform on any kind of structure or any kind of analysis, because you don't really need to know much about the loading conditions. You maybe just want to modify the E modulus, the boundary conditions, and see how much that affects the structural behavior. So in this case, I only did alpha equals to 0.5. So kx was 10 to the power of 0.5. And I obtained my first mode of vibration with that eigenfrequency and with 54% of the modal mass participating in that particular mode. So yeah, this is a script that is open source, and give it a go when you guys are interested in it. We will make sure it's easy for you guys to get started with this. Okay, so what does this result in? The not so famous S shape, which we will look more into details. But basically we can see that I have a logarithmic x-axis, sorry, where the power of the 10 to the power of alpha is indicated in the E plus. Also, we can see how the frequencies are changing between the first mode of vibration, the second, and the third. But there is something happening in the first mode. That is something we for sure can see. And what we can say is that for lower stiffness on Kx, we get the lower eigenfrequency. And when we increase the stiffness value, we get a higher eigenfrequency. And there in between, we get this S-shaped behavior. Also, we can see that we have a lower bound and an upper bound, which is good to know when we are eventually going to perform the dynamic analysis. So Daniel, I know you know more about this structural behavior, the S-shape, so I'm going to let you add some insight here as well.
Great, thank you, Shahol. So great. So first of all, I really like to add that for me it's fantastic to hear that the industry is actually going towards this direction. So programming behind your models, that this is pretty much the same approach that we have in the academia. And also we go from behind, maybe using MATLAB or Python, either from several platforms, or we actually just program our own structural analysis program. And then we pretty much would like to sample. We really like to know how is our system behaving. So let's go for the fundamentals again in this one. So first of all, we have performed just an eigenvalue analysis of this particular structure, and you can see on the right-hand side pretty much the first three mode shapes of the system. So pretty much the lowest one, it's the first mode of operation, then the second and the third one. And well, one of the most important things that I would really like to add in this particular discussion is that we previously said from the conceptual design point of view that you should have expected something related like a clamp, well, sort of like certainly not a simple supporter, but rather like a clamp behavior, something close to this. Especially for the first mode of operation, you can pretty much see it that when it's sort of arriving to the boundary conditions, well, it's actually well far away from a simple supporter, rather more like a clamp behavior from the mode shape perspective. So that's pretty much something that you can see in the first, in the second, and in the third mode of operation. And this is pretty much telling you, well, what's your reference model closest to your actual problem. Now this is actually quite important. You need to have a reference model such that we improve the decision based on these ones, given that we have the particular problem now that you're pretty much solving. Now let's go to the plot. So pretty much what we have performed, it's assign a linear spring in the longitudinal direction of the footbridge, and this is pretty much located in the lowest part of the support in one of the sides, and we have varied the linear spring stiffness, and then we have pretty much sample how our natural frequencies are going to vary as a function of this particular linear spring. So as we have a quite experienced audience, I think we can increase the level again. Well, if you design a structure, let's say if you make a static design, you pretty much, well, you sort of know the boundary conditions, because in the worst case scenario, you will activate that boundary condition. Well, is that the case for dynamics? Is that the case for field bridges? Well, not really, not really. And why is it? Well, pretty much we have a loading that it's, well, in magnitude is not that high. Is more related about the frequency of that loading, such that we will achieve resonance, and then we have got a problem. So thinking in these terms, then let's say we go to the graph, pretty much the parametric analysis, the sensitivity analysis, in which we get this S shape of the first natural frequency of the system, and we see that it goes from something that is around 1.1 to 1.7 hertz. And then you say that the second mode of operation and the third mode of operations are actually not varying quite a lot with respect to this particular linear spring. So let's say this boundary condition that we have identified that has a great influence in the first mode of operation. So why is this important? So, well, the thing is, why is this important? Is that you are pretty much varying the natural frequency of your system. This is pretty much telling you how your system is bounded to be in between those two natural frequencies for the first mode of operation. So pretty much the lower and lower bound, because we have identified which was the degree of freedom that had the influence for this particular system. Well, and then you would like to go further on, no? This is quite important, because if you need to design, you need to characterize the natural frequency of your system, and then, well, if you go to the code, then the code actually allows you to reduce the applied load based on the natural frequency of your system. So as you are a well-experienced audience, I would rather say, well, as a researcher, I can tell you, I'm pretty sure you're able to find a construction solution that will allow you to actually have that boundary condition or something closer to that boundary condition, such that you actually improve the decision making of your model. So the thing is that if you use a simply supported, if you use a roller, this particular bridge, just for the static solution, that's okay, but you would not have that. And this is where the parametric analysis comes to be quite important.
Okay. good stuff. We will try to jump on. We have some more slides to cover. I was thinking we will maybe be able to come back to this slide because we want to give you guys a nice analytical example of what is going on. Before do that, I will just present how the dynamic analysis is performed in FEM-Design, and then we will jump back to that slide. So basically, there is a direct time integration scheme. There are two ones that can be implemented or used, which is a Newmark or the Wilson method. And what is good about both of these methods is that they are unconditionally stable and will not introduce any numerical damping or wear behavior. However, we still need to make a convergence study of the time step to ensure accuracy. And as a rule of thumb, the period divided with 20 is a kind of good estimate. In this case, I have been using 0.01 seconds. And what is good about direct time integration is that we are solving the equation of motion in every time step. So we are not doing any modal decomposition or modal analysis. And also we don't require an eigen frequency calculations before performing this. The next tricky part is the Rayleigh damping matrix, which is it's a good method to introduce damping, but it's a mathematical trick. And in this case, we wanted to damp the modes between 0 Hertz and 1.7, and we introduced a material damping according to Cetron 0.4%, which in this case will be a Kelvin-Voigt type of damping. So the alpha value will be 0 and the beta value will be calculated according to the formula. I just want to jump into the FEM-Design world and show this before we come back to the analytical solution. So we will have the Folke-Bernadotte bridge, which I will be explaining kind of rapidly. So we have a load which corresponds to the mode shape. So this is the first mode of vibration. This is a basic load case. And then we use the excitation force to define a sinusoidal load with a period of the resonant frequency, in this case 1.69 Hertz. Then we choose an appropriate time step and the amplification factor of the load itself. The scalar value of the load is calculated according to Cetra. And what we can find there is that based on the psi function, which is dependent on the structural frequency, we get different values. So as you remember, for the sensitivity analysis, we were somewhere in between 1.7 and 1.1, which means that we would be having a very high load from the crowd or a very low load. So this is actually where, as a design engineer, you can use the existing guidelines to manipulate your result if you can ensure that, let's say, your boundary conditions are acting as you want them to do. So if you would have a very good roller that would not give you any longitudinal stiffness, you could basically decrease the dynamic load case in this one. This is the table presented by me, and the psi value is very high, which means I get doesn't look like a high load, it's 6 Pascal, but in the dynamic world, this would give us high accelerations. Just back to the FEM-Design. We have defined the period of the sinusoidal load. What is left for us to do is to activate the time history excitation force and to define the Rayleigh damping matrix. So this is where the damping comes in. And as I said, we've used the Kelvin-Voigt damping, which is defined by using alpha equals to 0 and then calculating beta accordingly. Also, the integration scheme was chosen to the Newmark's method. And then basically we just perform the analysis and can obtain our acceleration envelopes, which will be shown here. So if we only look at the vertical acceleration, first of all, we see we have more or less a steady state response. And we can see that the acceleration is asymptotically reaching 3.1 more or less meter per second square. Just to go back to the PowerPoint, what I was trying to explain in words is that how you as a design engineer can be in these two domains. So either use a very stiff structure if you design it in reality so it will act like this, and the acceleration becomes quite high. But in the second case, if we have a very weak longitudinal spring, we get quite low accelerations. I know this is something you like to emphasize as well, Daniel. So please add some words here regarding these two, let's say, domains.
Yes. So the thing is that, again, going back to the parametric analysis, you see that this is where actually the code allows you from, let's say, a stiffness strategy perspective, just going back to what we have already discussed, to actually reduce the applied load. And pretty much that factor is related to the fact that if you're actually your pedestrians, your crowd is going to be synchronized or not. Of course, this is only related to vertical vibrations in this particular case. But then you can see that given that you have actually sampled this S shape, so you have pretty much sampled the behavior of your system varying from something like 1.1 to 1.7 hertz in the first mode of vibration. Well, many things can be done now. So pretty much what we're saying is that our system, our actual system, the one that probably as a designer you will be able to see after. Me as a researcher, I can just go there and apply one of my advanced, I don't know, whatever fancy method, let's say a complex exponential method to characterize the system. But for you as a practical engineer, this is very important because you don't have the structure yet, but you still need to make a decision. And the thing about the parametric analysis is that going from something like 0.1 to 1.7 and having this huge difference in, let's say, the dynamic response of 3.1 meters per square second to 0.5 meters per square second will actually tell you, well, if you will be able to actually fulfill the serviceability requirement that is pretty much required by, let's say, the Eurocode or the CETA or whichever design guideline you're using. So I would rather say that depending on the construction solution that you have actually provided, your natural frequencies can be bounded. And as long as you can bound those natural frequencies, you have actually increased the information of the system. You know now more such that you can make a decision on the dynamic assessment of your system itself. And this is due to the fact that, again, when you design for statics, the worst load case scenario will actually activate the boundary conditions. In dynamics, well, especially for footbridges, you will likely have a bunch of friction. And this is when the parametric analysis becomes important, because you know that for sure you will, well, it's very unlikely that you will have a perfect clamp or, let's say, a perfectly fixed boundary condition, but well, it's very also not likely to have a perfect roller. So you will actually be in between. And this is when you as a designer, you as a construction engineer with a lot of experience, you can come up with a nice construction solution that would rather be something in between. And then you can make the dynamic assessment.
Perfect. Okay, I think we can jump on to the next slide, which is, I know, a favorite of yours, Daniel. It's the hand calculations to basically verify hours of finite element modeling and finite element analysis. Just to know that you're in the right domain. So please give us a brief explanation about this, because I think it would be really appreciated by the audience.
Great. So we already said that this particular bridge in its first mode of variation is actually sort of a clamp behavior, or at least closer to a clamp behavior. So the thing is that I would rather tell you, before making a model, before even selecting the type of element, you must be able to actually get an idea of what's happening. And this is rather from the conceptual design point of view. This is, of course, if the structure is rather, well, sort of easy to idealize and have some reference case that can give you sort of a feedback of your system. So let's go to this simple hand calculations now. So pretty much we have the simplest equation that characterizes any dynamic system. So pretty much the mobile stiffness is going to be equal to the mobile mass of the system times the circular natural frequency squared. That's pretty much the first equation that you can see in the upper left hand side of the slide. Then you have got the total mass of the system, so that would be your linear density multiplied by the span length of the system. And then we need to compute the modal mass. Now we need to have an idea of the modal mass of our bridge. Well, if it's simple supported, we know that the modal mass of the system, it will be half of the total mass. And if it's clamp, well, this one you would need to compute a bit more, but that's around 3/8. That's around 40% of the system, more or less. But this is in a very idealized case, no? But it's good to have these values, to bear these values in mind, because they will give you information about your system. And well, and then we have the classical steady-state response of the single degree of freedom system when resonance has been achieved. No? So we have got accelerations are equal to 1/2 divided by the damping ratio of the system, and then multiplied by the relationship between the mobile force divided by the mobile mass of the system. You need to define the mobile force. So if you define the mobile force, let's take the center now to have a reference, and then we go to our particular case. So if you define the mobile force using a sine shape, that's pretty much a simple supported beam, what you would find in the set of examples. That factor is going to be 2L/pi, and that's the factor you need to multiply the amplitude of your load such that you will get the mobile projection. So that would be your mobile force applied. If it's a clamp, well, that's different. You would just need to solve. We can increase also the level here. You just need to solve the integral for the motion, and then you will get the coefficient that is exactly span length over 2. So if you go to the right-hand side, you can see that the mobile force is equal to our pressure load, so 6.36 pascals, multiplied by the active area, so that's 300 square meters. Then we divide that one by the span length of our bridge, 98 meters, and then we get the load, the linear load that's being applied. Then we need to multiply by the factor to get the mobile force, that's span length divided by 2, and then we get 1,285 newtons that are actually being applied. Also for the mobile mass, then we compute the total mass of the system, roughly speaking 98 tons, multiplied by 3/8, and then you get around 36,750 kilograms. And since this is a steel structure, very lightly damped, that's around 0.4%. That's what pretty much the searcher will suggest you. Very simple, straightforward, and literally just evaluating the acceleration, you will get, roughly speaking, 3.24 meters per square second. So beforehand, that's just not making any models, you should be able to more or less estimate the order of magnitude of what you're expecting. Of course, this is based on an idealized case that in our particular example, we're taking the clamp beam as the reference because our system is rather far away from a simple supported. And then you get this number, not to get an idea of it. And then we need, of course, to check consistency, so how close we are now. So, and then if you actually compute the steady-state response, which in this case, Shahol has used data time integration for it, using FEM-Design, then you get 3.1. That's, well, very good.
I'm impressed by the hand calculations. What can we say about the finite element model? I hope it's as impressive as the hand calculations.
I think the finite element model is quite. Oh, I think it's pretty good. I think we're on the spot. Especially since actually this particular case study, at least from the Royal Institute of Technology perspective, so from KTH, we're actually publishing a conference paper out of this particular bridge, and we actually characterize the dynamic system, the dynamic properties of this system. again, we have an experienced audience, and pretty much this is parametric design, so we can go a bit deeper. No, so we were actually using genetic algorithms to actually, well, feed in a better way our system, and then we using aerospace techniques, sort of complex exponential methods for. So that's pretty good.
Okay, we're running out of time, so we'll try to wrap this up. Just some teasers. Future webinars, we will try to cover some railway bridge dynamics, and we're not speaking about lightweight structure there, but instead heavy loading from trains.
Heavy loading.
Yeah, exactly. So we will try to cover a topic about that in the future. Just some final conclusions. What I want to emphasize is how the FEM-Design API can be used for any parametric study to investigate the effects of critical parameters. In this particular case, it was a dynamic assessment, but it can be used to approach any kind of problem. And finally, some future work. I want to promote some bridge trainings we will be giving both in Stockholm and online. And also, if you guys are interested in exploring FEM-Design, and if you have not used it before, a trial or a demo, so get in touch with me in person, and I'll guide you guys. And Daniel, you also have some work you can promote.
Yes, so in my particular case would be the conference paper, so titled Full-Scale Tests on a Lightweight Fit Bridge, the Folkebernabad Bridge. And this is going to be a conference paper actually published in Cape Town in South Africa this year, the conference SMZ. And as a researcher, as a PhD candidate, well, we represent academia, so we're actually more we're delighted to have people with doubts or that would like to make a sort of a question regarding a particular system, where you guys are more than welcome to contact us, especially if you're in Stockholm as well. You can pass by the office.
Okay, guys. So I think we are done with speaking. I will pause the recording.